Okay, let's continue. More definitions on sequences. Okay, so last time I told you the relationship between logs, exponentials, polynomials, factorials, and that variable exponential thing, whatever. Okay, an important sequence. It's called the geometric sequence. It is with the form, just like a geometric series, which I introduced to you before. AR to the n. Right, that's called a geometric sequence. A, R, constants. And we know that it converges on that interval, diverges otherwise. In fact, the limit as n approaches infinity of a r to the n. It's 0 if your r is less than 1 in absolute values, and it's actually a if your r is equal to 1. Okay. Another important sequence that we're not your textbook doesn't mention this, but pretty much everyone will expect you to know what it is. It's the arithmetic sequence. The thing is, the geometric sequence is really important because as a series it behaves nicely, but an arithmetic sequence, if you throw that as a series, which we will do later, it'll always diverge, so that's why they don't really focus on it. The geometric one has a chance of convergence. Sequence that looks something like a plus n minus 1 times d. N goes from 1 to infinity. First term, this is called the common difference. So it sort of looks like the equation of a line. It's called an arithmetic progression. I won't really say any more about it because for a series, which is where we're going, it's not very useful. It'll always diverge as n goes to infinity. One other thing with sequences, what we want to talk about, monotonicity. This idea is going to be important when we talk about alternating sequences and the integral test later on. So the sequence is said increasing if an plus 1 is greater than an. It is decreasing with an plus 1 is less than A. Of course, there might be a sequence that it changes its behavior. Sometimes it's increasing, sometimes it's decreasing, and so on and so forth. I might not say for all n, maybe for some range of n here, because I want to really emphasize the difference between monotonicity. Say for some range of n. So I can say it's increasing for n between blah and blah, or it's decreasing for some range of n. If such behavior is uniform, i.e. happens if either behavior is uniform, happens for all n, we say the sequence is monotone. It's always doing the same thing. So we call it monotone. So a sequence can be monotonically increasing which means it's always increasing. The terms keep getting bigger and bigger and this behavior does not change, or monotonically decreasing. The word monotone just means it's doing the same thing uniformly. In the future, there are going to be cases where it's important for us to know that our sequence is monotonically decreasing. So that's why I had to give you that definition. Other formulations, of course, you can use the derivative. Right, so I can say an is increasing where a prime is greater, an prime is greater than 0. Right? Remember, we think of an as a function of n. So if I take the derivative with respect to n, and I always get a positive number, that means it's increasing. An is decreasing. Where an prime is less than 0. Okay. That's what I want to tell you. We're almost done with sequences. They're not a big part of what we're doing, but they will inform a lot of what we do later. Let's just do some examples here. Are these monotone? If so, are they increasing or decreasing? A.
Decreasing?
Hmm?
Is it decreasing?
Decreasing. an equals 1 over n is monotonically decreasing. Why? Because in one case, notice that 1 over n plus 1 is always greater than 1 over n. Right? Always less than 1 over n. So each new term, this is the an plus 1 term, is always less than the an term. 2, if I take an prime, I would get what? Huh? Minus 1 over n squared. N squared is a positive number, so I'm taking the negative of a positive number. This is always less than 0 once my n is 1 or bigger. What about the other one?
This is for positive n values only, right?
Yeah, I'm doing a sequence with the n greater than or equal to 1. What about B? How do you know it's monotonically increasing? You can look at A prime would be what?
1 plus 1 over n squared.
1 plus 1 over n squared. Right? So as n gets larger, what happens? When n is 1, what do you have? 2. Does it get larger or smaller as we increase n?
Eighth level one gets lower.
It's slow. It's positive, that's the important part.
Oh.
So that's actually increasing. What else do I want to tell you about sequences? Last thing, remember your limits. Right, so, and I'm talking about the limits from single variable calculus. They will be important. Here and in the future sections that we will be doing. Right. So i.e. remember for things like L'Hopital's rule. Things like limits of ratios of rational functions, ratios of polynomials. Things like the special trig limits, which we've also been using those earlier when we're actually doing limits. So those are things like you should know, like limit of sine n over n equals 0. Things like that you shouldn't really bat an eye to figure out. What about limits of rational functions? How do those work? Tell me the quick rules. As we're going to infinity or negative. Hmm?
The coefficient is one of the largest ones.
No. So I'm looking at this guy. I'm taking the limit as n goes to infinity of something like p of n over q of n, where these guys are polynomials. What are the rules? What are the possible outcomes here?
Well, depending where the higher power is.
Okay, what is the...
If the higher power is in the denominator, it goes to 0.
Right, it's 0 if the degree of Q is greater than the degree of P. What else?
It's infinity if P is greater than Q.
Well, it's plus or minus infinity, or it could be
Yeah.
minus. You have to watch the signs. If the degree of P is greater than the degree of Q, just watch your signs, be careful. And what's the other option? Huh? As we're going to infinity,
It goes
it'll always exist.
if the degree is the same, it'll go to a constant.
So this is if this one is bigger than that one, if the other one is bigger. What if they're equal? What happens? It's equal to the ratio of the leading coefficients. Right, so you look at the coefficient of the highest power on the top divided by the coefficient of the highest power on the bottom, and that's going to be your answer. Right, things like that I expect you to remember. Won't really go more into that. Okay, great. That's what we're going to do on sequences. Not a very hard chapter. The hardest thing you're going to do in this section is take limits, right, to figure out if something converges or not. It's going to be an important idea, as you'll see later, but I'm not going to spend any more time on that. Right now we're going to get to the meat of the matter. What's really important for us is series. This is what you're going to be tested on, guaranteed to come on your final, both in the compulsory section and in the optional section. Now remember what I said, approach this with the mindset that it is easy. It is a Calc 2 topic. It just feels different, and it might feel harder because it seems unfamiliar compared to what we've been doing, but really it's just recognizing forms and applying formulas to it. So we're going to talk about series, and really we can do them all at once, based on, remember that sheet I gave you last time, the table of series? Make sure you have it. We're going to be using it. With the power of that sheet, we can actually take care of 3 sections all at once, just go knock them out. Because these all talk about the test. Basically, that table summarizes these 3 sections, and we're going to do that. So, some preliminaries. Talk about definition. Talk about what a series is, how we can think of it. A series is a sum of the terms of a sequence. So, if AN is a sequence, series involving AN is that summation in front of your AN, and it pretty much tells you add up all these terms in the sequence. So remember, the sequence was just a list of numbers in some definite order, which is defined by the formula given by AN. However, whenever I put this summation sign here, it means add all the terms. Right? So take that first term, add it to the second term, add it to the third term, add it to the fourth term, etc. Right? Remember, series can be finite or infinite. Right? So a finite series is just a guy that adds up a finite number of terms. So from n equals 1 to some finite constant. Finite positive integer. Right? So that's called a finite series. Infinite series, which are the far by far the more, the ones we are more concerned about is when it goes, we're adding an infinite number of terms. So a finite series is just when we're adding up a finite number of terms. Infinite series is when we're adding up an infinite number of terms. So we sort of think of it as just summing the terms of a sequence, right? So our sequences are going to, understanding what sequences are is sort of important. What else do I want to tell you about series before we jump into it? You might see me write things like this. I'll just write the number here instead of n equals, or just the sum of a n, if understood. It's not exactly formal, but I'll do it just so you know. Just be aware of that. Yeah?
So, what does LA does not equal Y?
Come again?
You said when LA does not equal Y.
When L.
Oh, that's lazy. Never mind.
When lazy. Yeah. Yeah, you get lazy. You got too lazy to read just now. That's what I'm talking about. Yeah. Okay, what else do I want to say? Okay. Some definitions. I mentioned this at some point, but I just want you to write down the formal definition so you know. Some series do what we call converge. That is, this is chalk. It's horrible. They sum to a finite number. Many times. We would want to know that the series converges. But not necessarily what it converges to. Sometimes you can find out, other times you can't. Did I give the definition of what converges means specifically? So let's talk about partial sums and what it means for a series to converge, right? So basically these are what a series are. The sum of the terms of a sequence. You can have finite ones and infinite ones. The infinite ones are the more the ones we care about the most. Sometimes series, whether finite or infinite, they can converge. That means they will add up to a finite number. A lot of times we want to know when this happens. We don't care what it adds up to. Sometimes we'll care about what it adds up to, but not always. So that's necessary. Then convergence. Let's talk a little bit more about that. We say a sequence, a series, I don't know who ordered the chalk this one. A series converges partial sums converges. Here's one of the reasons why you will want to know what the limit of a sequence looks like. Let's talk about partial sums. A partial sum is a sum of the first, let's say, n terms in a series. The terms are usually denoted Sn. Try to get through this. So you really want to get to the fun stuff today. Okay, so let's do an example. Yeah, let's actually do an example. Example. Let's look at this series. 1 over 2 to the n. N goes from 1 to infinity. Okay. So this is like my an here. Right? So I'm going to describe how we can figure out that this guy converges. We can even figure out what he converges to. But I'm going to do it in the partial sums way of doing it, how we sort of think of this guy. All right, so the idea is to figure out what the sum of the terms are doing, and then create a sequence from that, and we can figure out what the sequence is doing. So this is in general how we can figure out what a sum converges to. So let's do an example. Let's compute the partial sums. So, for example, we know what the sum of this is, right? So 1 over 2 to the n, this is just a half, right? From 1 to infinity. It's a half plus a quarter plus an eighth plus a 16, right? So the partial sums just mean I'm summing up a finite number of sequence terms, the first n terms. So for example, S1 is what? It's just a half. This means the sum of the first term. Sum of the first term. Which sounds kind of weird, but that's true. Okay, S2 would be a half plus a quarter. Right? What is that, by the way? 3/4. So this is the sum of the first two terms. S3 would be a half plus a quarter plus an eighth, which is going to be what? Huh? 7 over 8. This is the sum of the first three terms. Okay. S4. One more so you get the idea. What's that S4 going to be? Write it out. 1/2 plus a quarter plus an eighth plus a 16 equals 15 over 16, right? Dot, 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 right? So this is basically, each of these are called a partial sum, right? Some of the first terms, some of the first two terms, some of the first three terms, some of the first four terms. What about the sum of the first n terms? Could you figure that out? Now remember what we did the first day we started talking about series. We said if we had a list of numbers sort of following a pattern, if we can decipher a pattern, could you actually come up with a formula for it? Could you come up with a formula for a sequence that goes from a half The second term is 3/4. The third term is 7/8. The fourth term is 15/16, so on and so forth.
2n? No, n minus 1.
What's the denominators doing? 2, 4, 8, 16, right? What's the denominator doing? 2 to the n, right? Starting from n equals 1. What's the numerator doing?
2 plus 1.
No, minus.
Minus. Notice that the numerator is always 1 less than the denominator, right? It's 1/2, 3/4, 7/8, 15/16. Right? So looking at the list of the sums, I can actually generate a formula for it. I can generate a sequence. This guy is called the sequence of partial sums. Right? So at any given point, at any time I stop in this sequence, if I say the first 100 terms, I can calculate the sum of the first 100 terms. Just plug in n equals 100. I can calculate the sum of the first 1 million terms, plug in n equals 1,000,000. The first trillion terms, plug in n equals 1,000,000,000,000. Right? At any point, I can say, what is the sum of all terms up to that point? And all I have to do is look at what this sequence is telling me. Right? So now I went from this notation here of a sum, which is just an infinite addition, but then really I can cut off any finite part of that sum and describe it with a sequence. And now what we can say is, this sum is an infinite series. This is, right? So we're going up to infinity. So what do you think the answer, if an answer exists to this guy, what would he have to be? In general, in terms of a definition. Right. You let n go to infinity because we're letting n go to infinity, right? We can conclude here. Not going to go into all the theory, like all this had to be proven rigorously at some point, but that's for an advanced calculus course. We're not going to do that. We can conclude that the sum of this guy, 1/2 to the n goes from 1 to infinity, is really just the let n go to infinity of this sequence. Now, what do we know about, from what we know about limits, we know that this is actually 1. Right? So faced with a series, I can do something like this. I can figure out what are the partial sums, right? What are the first n terms? If I can find out a formula for it, that's great, because I can just plug it now. I can just plug in my limit and figure out what that formula is going towards. Right? Of course, if it's a finite sum, then I'll just plug in the very last number of terms, right? So if it was just series n goes from 1 up to 25, what's the answer? Just plug in 25 here, and I'm done, right? But since n is going off to infinity, I just take a limit, right? And whatever that approaches is what we consider the summation to converge to. So the series of 1/2 to the n converges. Furthermore, I know what it converges to. It converges to 1. So if I add up an infinite number of terms where each term has this form, the answer is actually going to be 1. It's going to be a finite answer. So that actually works in general. That based on the definition, that's how we figure out a series. However, of course, there's always a however. In general, coming up with a formula for Sn is difficult. Right, that one was actually a pretty easy example. This is why we need the series test. This is why I gave you that table. This table can tell us about convergence without us actually knowing what it converges to in most cases, but we can know it converges. It's not an exhaustive list, but yeah, you had a question?
Yeah, before you said it has to converge, it has to go to a finite number. Can it converge to infinity?
No, we say it diverges if it goes to infinity. Right? So if this limit goes to infinity or does not exist, we say the series diverges. Right? Yeah. So we have many tests. This is not an exhaustive list, as I was saying, that can help us determine convergence. And that's basically what these chapters are about. What else do I want to do? Yeah. So these sections cover these tests. This is not a test, but one technique that's not in your table that's discussed in the text. There's something called a telescoping series. I have to tell you about this separately. It basically looks also at the sequence of partial sums, so let me just do that. Just so you know, this involves partial fractions. Yay! Just so you know. So let me give you an example here. Example. Determine the convergence of a series from 1 to infinity, 1 over n times n plus 1. Well, I gave you the hint. Partial fractions, how would it look? How would we do it?
Something over n, a over n, and b over.
Right, you'll have something over n plus something over n plus 1. All right, what's your a? What's a? A is going to be 1. B is going to be what? How'd you do that? Did you do the whole thing?
I did that multiplied out.
Okay. Remember there's a trick the shortcut for this, I don't know if you guys remember this from Calc 2. But what you can do is to figure out whenever your terms are linear in the denominator, you can always do this trick. You figure out what makes one denominator 0, right? So like for example here, n equals 0 makes this denominator 0, right? You go over here, you cover that part up and you plug in n equals 0, right? The result is 1. A is 1. What makes this 0? N equals minus 1. Go over here, cover that up, plug in n equals minus 1. Minus 1 is the result, right? So you can get to this a lot quicker when your denominators are linear. That's a part of a theorem called the residue theorem, which you learn in complex analysis, which I'm not going to get into. It works in general, but for the linear case, it's really easy. So that, at least, I told my Calc 2 class, I would assume you learned it in your Calc 2 class. Okay, so that sort of saves you some work, so you can just get through these problems quickly. Okay, so we know that this is true. Therefore, the summation of 1 over n times n plus 1 is equal to the summation of 1 over n minus 1 over n plus 1. Right?
Bless you. Good, man.
Now, how do we describe what this series is doing? So here's how we handle this. Start writing out some terms, right? What does the first term look like? 1 minus a half. That's the first term. What does the second term look like? A half minus a third. What's the third term look like? A third minus a fourth. Fourth term? Do you guys see the pattern? Okay. So we know what the first few terms look like. What are the last few terms look like? What if I am 3 terms away from the back? Like the n minus third term. What would that look like?
1 over n minus 3 minus 1 over n minus 2.
1 over n minus 3 minus 1 over n minus 2. Right? Plus, what does the n minus second term look like? One over n minus 2 minus 1 over n minus 1 plus n minus first term one over n minus 1 minus 1 over n plus, let's look at the nth term. It's just 1 over n minus 1 over n plus 1. Okay. So basically what I'm doing is I'm thinking of this sequence as a limit. As n goes to infinity of the sum. So I'm thinking of it in terms of its partial sums. It's the trick here. So again, I look at the partial sums, summing up to n, and I'm going to let that n go to infinity. Basically what the terms would look like is this. Right? So now you sort of see a pattern. Right? What's going to happen here?
All the terms cancel.
Certain terms are canceling. Do all of them cancel? Well,
first
I know
one
the
allows.
1/2 cancels, the 1/3 cancels, the 1/4 cancels. The next term is going to cancel the 1/5. Right? Go up here, what's going to happen? Sure, the n minus 2's cancel, the n minus 1's will cancel, the 1 over n's would cancel. This guy is going to be canceled by the term, the second term in the previous term, so that's going to cancel. Who's going to cancel this guy? Nobody, right? You would have to go back. So basically, this whole thing simplifies into this guy. N goes to infinity. What are we left with? 1 minus 1 over n plus 1. Which equals to what? Okay, limit as n goes to infinity, the result is 1. Therefore, the series of 1 to infinity of 1 over n plus 1 actually converges, and it is equal to 1. Some remarks? Series that behave in this way are called telescoping series. That's the first thing. One, how do we know we have to look out for this? One hint that you have to do a telescoping series, if given a series of the form P of n over Q of n, these guys are polynomials, and asked to give the exact sum. These are just some options that you think about, right? So here's the thing. Remember, series in general, I mean, I'm really glossing over this, but in general, they're really hard to actually calculate, right? So if someone gives you something like this and say, hey, calculate it, it means this particular one is easy to calculate, right? And one of the easiest ways to do something like this in general is to sort of split it into partial fractions, right? 2 is if given something like the series of P over n over Q over n and Qn factors. That might be something else that you want to look out for. Because once your denominator factors, you can split into partial fractions. And of course, all the rules of partial fractions applies. You have to look at the degree of P, make sure it's smaller than the degree of Q, etc., etc. Okay. What else? So once they ask us to find the exact sum, that's sort of a hint when you have a ratio of polynomials. Or if you're looking at this and they don't really tell you to find the exact sum, but they actually evaluate or determine convergence or something like that, you can do this if you notice that Qn factors. Where else we do? If they mention telescoping sum outright, you just know. Which very rarely happens, but it does happen. So that's a very famous kind of series called a telescoping series, and that's actually how you deal with it. You sort of write it down exactly how I wrote out this example here. I was sort of teaching you something while writing it out. Same sort of method would work. You'd have to be good at partial fractions. So if you don't remember that, have to look over that. You can watch my Cal 2 videos on partial fractions where I go over it from scratch. Yeah, so that's just a very important thing that I had to throw in there because it's not in your table. I'm a bit out of it today. I keep thinking of things I should have told you in hindsight. Let's see. Okay. Also want you to recall some properties. Recall some properties. So make sure being out of it, I'm too excited to get to the actual meat of the matter. If the series of AN and the series of BN converge, then so does a constant times AN, and the sums of them AN plus or minus BN would also converge. Or the sum of a constant times AN is just the constant times the sum of AN, whatever you know that answer is. And the sum of AN plus or minus BN is just equal to the sum of AN plus or minus the sum of BN. You just sort of add the answers together. That'll be fine. Not too hard to see that. Okay, can we get to the test now?
How does that be applied to the what we just did? Because of the 1 over n minus 1 over n plus 1, then you could have separated the two from series and then calculate each one separately?
Each one separately does not converge.
Oh, okay. Gotcha.
So the previous example would not work because we don't have this condition fulfilled. Each one separately is what we call a harmonic series, so it wouldn't converge, so we couldn't use this. They actually needed each other to actually work out. It's because one undid the damage that the first one did. So that's how that one worked out. Okay, I think we can jump to the test now. So some of these we actually covered already, like the geometric series, the kth term test. I sort of did a p-series test, but we're going to go through pretty much this whole table. I'm going to give you a bunch of examples to use for each one of these. And we're going to talk about them, how they would show up in a test, what you have to think about, what you have to see, that sort of stuff. Yeah, so let's actually do that. So before, when we were doing our series corner whole thing, I sort of explained to you the importance of series. For example, something like the integral is really a series, right? So knowing if something converges could be equivalent to knowing whether you can integrate a function or not. So it's actually pretty important. Integration is pretty important. And series are pretty important, which you won't fully appreciate it now, but later you will. Especially if you go into more mathematical things, like depending on where you're going. If you're a math major, you'll realize just how important. Probably, if you're into electrical engineering, you'll also see them in great detail. You have a lot of math for electrical engineering. But yeah, let's continue. Let's talk about the series. Okay, so let's look at the series test. I probably put these in a different order. So one, let's look at the kth term test. AKA the nth term test is if n is used as your variable. AKA test for divergence. That's the first one we're going to look at. So the series tests are pretty much, they're shortcuts, right? They can tell us when a series converges or not. just by going through these tests. We don't have to worry about finding partial sums or doing a telescoping thing. We can just actually apply this test to a series if it is in the right form for it, and we can determine whether it converges or not. This guy works for any series, right? So this guy is always applicable. It should be the first thing that you look for, so I'll also put that as a bullet point. It should be the first. That's why I'm reordering it in the table. Series test you think of applying. So here's the idea. Here's how you're sort of going to be tested. How it's going to work is, you remember how in Calc 2, like problem 2 was always this question where they gave you a bunch of integrals and you just have to do the integrals, right? And they didn't tell you, oh, use by parts, use this, use that, right? They just say, compute these integrals. Something very similar is going to happen on your test, right? And on the final, right? They're going to give you a bunch of series and they're going to say, evaluate the series. If they converge, if they diverge, let us know and tell us why, right? So that's what it's going to be like. So you're going to be faced with a whole bunch of different things, and then you're going to have to figure out what test to apply, you know, what to do, all that sort of stuff. So just like how with integrals, there was a hierarchy that you had, right? Right? You're faced with a bunch of integrals. What's the first thing you think about? Power rule, right? That's the very first thing you think of applying when you see an arbitrary integral. Does the power rule work? No. What's the next thing you think about? Substitution, right? That's the next easiest technique. Substitution doesn't work. Next thing you think about, then you start to think about, well, if there's a product I can use by parts, right? Or you know the forms for by parts. Oh, you know, if there's that form of x squared plus a squared, it can use a trig sub. If there's no odd power elsewhere, right? There's some sort of, like a list of things you go through, right? You don't look at a random integral and think partial fractions, right? It's never the first thing you think about. You always look for the easiest way, right? This guy is by far the easiest thing to apply. It's the guy you need to look for first, the test for divergence. Basically, that's the guy that says if your limit doesn't go to 0, your series is not going to converge. Limits are something we know very well at this point. We've done them in Calc 1, we've done them in Calc 2, we've done them in Calc 3, even the multivariable case. So they are easy to apply. It's easy to just look at it and tell, oh yeah, that's going to converge or not. So it's the first thing you should think of applying when faced with any random series. It's the first thing you're going to look for. You're going to check the limit. The test states, given the series from 1 or whatever of an, if the limit as n goes to infinity of an is not 0, then the series diverges. That's the test. Important remarks. Very, very important remarks. Something you need to know about this test. Do not mix it up. Very important. It's called the test for divergence for a reason. This test tells you when a series diverges. It cannot tell you if it converges. Right? That's a very important thing you have to note about this test. The converse is not true. So basically, the test for divergence tells you about divergence. You have a series, you notice that the limit of the terms do not go to 0, you can say, oh, the series diverges. If the limit is 0, you can make no conclusion, right? That's very important, that you never use this to tell if something converges. It cannot tell you, right? So there are some important examples, which I believe I gave you last time. Some important examples to keep in mind here. Is one, there's the so-called harmonic series. It's a super important series, it shows up all the time. This is the series of the form n goes from 1 to infinity of 1 over n. Right? This series, this is just something you should know automatically. This series diverges. It's perhaps the most famous divergence series. But you would notice that the limit of 1 over n is actually 0. Right? But you can prove that this diverges. There are a multitude of ways to prove that this diverges. Right? I'm sure your textbook did at least a couple, and in the future sections it showed you some more. Right? But this is a very famous series. It diverges. However, the limit is equal to 0. That sort of tells you if your limit is 0, you can't really say anything. You can't really tell if it converges or diverges. There's another series, while if I look at 1 over n squared from 1 to infinity, this series converges. And the limit n goes to infinity of 1 over n squared equals 0. Right? So there are cases when you get 0, but it can actually tell you nothing. It's possible for it to diverge as well as converge. Right? So if the limit is 0, there's no information. You have to do something else. What's important is when the limit is not 0. That's what this test tells you about. Right? It tells you about divergence. As long as the limit is not 0, then we know it diverges. If the limit is 0, it could really go either way. Right? So that's something that's very important for you to consider with this test. In fact, we're not going to learn this, but it's actually pi squared over 6, believe it or not. It's really weird, but that's the answer. Let's look at another one. Okay, let's look at another example here. N goes from 1 to infinity of 3n squared plus 2n plus 1 over 4n squared minus 3. So you see that, what do you think? Now you may slip into bad habits and you sort of think, oh, it's a ratio of polynomials, maybe partial fractions will work. But you'd immediately notice that the denominator does not factor. But however, if that's the first thing you think, you have not remembered your training. The first thing you will think when you see any series is the test for divergence. Turns out here that if this guy is an, what's the limit of an? Altogether now? 3/4. Not equal 0. The series diverges. Another example. I'll probably give an example so you can just. Oh my god, it's a trig function, there are factorials in it, oh my god. It's the first thing you think about. Limit. Last time we learned that n to the n overwhelms n factorial overwhelmingly, right? So if we're going to infinity, what happens? The denominator will overwhelm the numerator so that it's going to go to 0. Cosine of 0 is 1. Not equals 0. Divergence. Right? Applying the test for divergence, it's a one-liner, right? And it's the first thing you always look for. What is the limit, right? Normally you can tell, you see that, limit is 3/4. You just look at that and you know, because you're awesome at Calc 2. It's right in the back of your mind at all times. See that, you remember how these guys behave. That's not going to go to 0, so that diverges. So I can tell when something diverges. I can't tell when something converges, and I can do that simply by considering the limit.
Do you make right by the end-term test or by the test, or just know
I would expect you to state the test in general, right? So the series diverges by the divergence test. Usually the question will be phrased so it's going to say justify whatever you're doing. So you'll just state the test and that'll be good enough. So those are examples for the test for divergence. I gave you several other examples in our series corner last time, so you can look over those. You'll have tons of examples in your text as well for the homework. So with that, we move on to the next guy. I also spoke about before. This is geometric series test. This works on series of the form remember A, R are constants. Right? So you'll notice in your table there's a column that says when to use. Right? Now in the geometric series part, it says when to use is when your series looks like this, right? That's when you use it, right? And then it tells you what conclusions you can make based on things that happen, right? So the table is really nice to have while you're doing the homework. Just keep it beside you while you're doing the homework. After you do a bunch of problems, you'll memorize a lot of the tests like automatically. So it's very important that you remember A and R are constants. N is the variable. It's the guy that the series is counting. So the conclusion we can make here is it's A over 1 minus R if your R is less than 1 in absolute values and it diverges if R is greater than or equal to 1 in absolute values. Note in this case the limit of the AN term would not be 0. Right? So even if you see this where your n is, you can see this, it's a geometric series, but you can still use a divergence test on some of these. If your n is bigger than 1, bigger than or equal to 1, the limit won't be 0. So. And this general form, let me make a general statement. In general, the forms given here and in the rest of the test, forms given are forms you should be simplify to. They may not be given exactly as they may not given exactly as shown. Right? So that's one of the parts that makes this whole thing sort of tricky. You might have to simplify and see things, which it's not an unusual thing. You did this with integrals as well. So as I told you, if you sort of think of things like in the linear fashion, like this could be mn plus b, right? That would still fall under this because you'd be able to simplify this to like a r to the b times r to the n to the n, right? Where this guy is like your a constant and this guy is like your r constant, right? So as long as you can simplify to get that form, that's okay. It might not be given to you like that. It might look very different. Still a couple examples here. And again, for geometry, I think I gave you tons of examples for geometric in the last series going. I think it was like the second series going. Let's look at this one. Okay, what do you think?
Try to simplify.
Huh?
Try to simplify it by separating the terms.
No? Is that what you think?
Well, okay.
What?
Do the test for divergence.
Divergence. Divergence is always the first thing you think about in any case. The limit here goes to 0, so the divergence test is inadmissible. First, think divergence test. Here, limit of an equals 0, so can't use it. Okay, now what do we think? Right? We know that e is 2.71828, right? So here I have an exponential where the base is 2 point something. On the bottom I have an exponential where the base is 4. So the bottom is going to overwhelm the top. The limit actually goes to 0. Okay. So I look at that, oh, the limit goes to 0. Okay, now what? Well, I noticed that there are some things raised to the nth power. And I know that I have the geometric series where it talks about forms of things raised to the nth power, but it doesn't look exactly like that form, so what do?
You make it look like that?
How do we make it look like that?
You separate 1 over 4 and
You can separate them. 1 over 4 to the n plus 1 plus e to the n over 4 to the n plus 1. How can you write this guy?
1 over 4 to the next one.
Huh?
1/3.
This one?
Well, so it's 1 over 1/4 times 1 over 4 to the n.
All right, this is 1/4 times 1/4 to the n plus
1/4 times e over 4.
1/4 times e over 4 to the n. Let's move over here. Let me just rewrite this. 1/4 times 1 over 4 to the n plus 1/4 times e over 4 to the n. Notice that this is just a sum of geometric series. I can, using my properties that I mentioned a bit earlier, I can split the sum across these two. It's 1 over 4 to the n plus the series of 1 over 4 e over 4 to the n. 1 over 4 is a constant. This is also a constant raised to an nth power. This guy is like my a term. That is like my r term. Similarly, this will be my a term. That will be my r term. Right? Because my n starts at 0 will give me that a. Remember, one thing you want to think about a is it's the first term. Right? So, what do you think about now? Will it actually converge? How do I know? You look at the r term. Notice here your r in absolute values, it's less than 1 because it's a quarter. Same thing here. Remember, e is 2.71828, which means that in absolute values, my r is less than 1. So both will converge separately. And I know that if two series converge, then their sum will converge. This would converge to what? A over 1 minus r. A is the first term, which is a quarter, over 1 minus quarter, plus this one. A is a quarter, over 1 minus e over 4. A quarter over 1 minus a quarter is what? A third. A quarter over 1 minus e. That's actually the answer. So this guy converges, and in fact it converges to that number. Yes?
Sorry, could you expand on that, those numbers?
The 4 to the n plus 1, I wrote as 4 times 4 to the n.
Okay.
And then I factored off the 4.
Okay.
Yeah. Laws of exponents, you have to remember that too. Yeah. Remember all the math you've ever done, ever. Okay, so slight variation here. Just a little slight variation. What if I gave you exactly the same series, but now n starts at 2? We know it's going to converge, but how do we figure out what it converges to? So we're going to go in here, we're going to have n equals 2. Let's just jump to this guy, to infinity. Okay, at this point I can't say that this is my a because it's actually not my a, right? So what does it have to look like? How can I fix this?
You just plug in 2, you get 1 over 64.
Right, so I know it sort of looks like that form. It should be an a and an r, but it's not exactly. However, here you just compute it. You know that a would be when you plug in n equals 2. Right, so you plug in n equals 2, you get a quarter times a quarter squared. Right? So that's just 1/4 cubed. That's going to be your a. Your r is just a quarter. Similarly here, you're going to say your a is actually a quarter times e over 4 squared. Your r is e over 4. So ultimately this would equal a over 1 minus r plus this would equal to a over 1 minus r, right? Which will give you a different number. right? So that's a geometric series. As you can sort of see, it comes down to having the right form. You have to recognize when something can be simplified into a certain form that you have according to this table. Let's see that. Again, I did tons of examples on geometric series already. Let's talk about the integral test. Can be used when given the summation of an and an is continuous. So again, it works on very general kinds of series. Its conditions to use. One, an is decreasing. Remember, we spoke about what decreasing means. So as a sequence, it's decreasing. And b, an is easily integrable. That's sort of when you know you have to use this. So let's look at an example. Here's a series, n equals 1 to infinity, of e to the 1 over n squared. Oh, conclusion, type 2. I'm going to be a little informal here. Find the integral of an dn. They don't like to write like that. They write this as f of x dx, where you just replace all the n's here with x, whatever. You're just going to find the integral. And it has to be from the same thing. So if this is like n equals a up to infinity, this integral would have to be a to infinity. And given these two conditions, the series of an and the integral of an both converge together or both diverge. So this is called the integral test. Right? So faced with a random series, you look at it. First thing you look for, limit. Is the limit 0 or not? If it's not 0, you're done. Series diverges. Okay, what if the limit is 0? Then you have to move on. If you have a certain form like ar to the n, you know it's a geometric series, you apply the geometric series. If you happen to notice that, hey, that function is continuous and the integral is actually pretty easy for me to compute, of course you should know if an integral is, if it'll be easy to integrate something. Then, if the thing is decreasing, easily integrable, and continuous, you can apply what we call the integral test. It turns out that the integral will behave similar to the series. The integral will always give you a slightly bigger answer than the series, but they'll both converge. Once that guy converges, he's actually bigger than this guy, so this guy would have to converge. So that's basically the integral test. You integrate. Okay? So, what happens here? What's the first thing you talk about? No. Limit e to the 1 over n squared as n goes to infinity is 0. The top, the limit goes to 1, and the bottom, the limit goes to infinity. So this approach is 1 over infinity, so it's equal to 0. Test for divergence doesn't help. Also note, it's not geometric. How do I know it's not geometric? A base is the n, the power is a constant. It's the total opposite of what we need for geometric. The power here is 1 over n, it's not a linear power. We don't have linear powers and our bases are not constants. It's not geometric, right? Bases have to be constants and the powers have to be linear in order to be geometric. So it's not geometric, limit is 0, first two tests don't apply. However, this guy is actually decreasing. So then what we would do is, we'd think this in our heads, but we wouldn't really write it down, because then it would be a waste of space. So at this point, we're going to say, note, e to the 1 over n squared is continuous for n greater than or equal to 1, and it is a decreasing function. Now, in general, unless it's a really weird case, I will have faith in you that you actually know when something's decreasing or increasing, because I'm just a nice guy like that, right? So if it's obvious, which it's obvious in this case, the top is getting smaller, it's going to 1, and the denominator is going to infinity, it's sort of obvious that this is a decreasing function, right? So I won't require you to prove something like that. If it's really a mangled mess and I'm like, does it? Right, if I have to think, like, then you'd have to sort of justify it, which wouldn't be bad. Here you just find the derivative, you'll see that it's negative, right? So, yeah, but in general, you can just say, this is a decreasing function. Make sure you're right. If you say it's a decreasing function, it's actually not. Then you're in trouble, right? Then I'm going to like, try to pull one over on you. It's not going to work, right? Because I will know if it's decreasing or not, okay? So, but you need to write this down. I need to know that you're actually checking, you're actually looking for it. It's very important. Before you apply the test, you have to know what conditions have to be fulfilled. So I'm going to write this, I'm going to think, oh, find the limit. Oh, damn it, 0. Okay. Okay, I see things to powers. Is it geometric? No. Base is a variable, top is a constant, not geometric. Oh, wait a tick. 1 over n, what's the derivative? Minus 1 over n squared. Seems like a substitution can work. Is the thing decreasing? Sure, it's continuous and it's decreasing. I can apply the integral test. All right? At this point, we're like 2 seconds into thinking about the problem. Like all that happened in 2 seconds just now. Okay. Because we have like 5 other series to get to, right? We don't want to waste a lot of time on this. You're going to want to practice to the point where you can just see this like right away. Okay, so at this point, you're going to say, okay, let's look at the integral from, what is it, 1 to infinity? I mean, your book replaces this with x. Okay, it's not really necessary. Do it with respect to n. I don't particularly care. Right, so this is an improper integral, which technically it means that you're taking a limit. But again, we're big kids now. I'm sort of going to know that you're taking the limit. I'm not going to sweat it too much. So technically, you're taking a limit as n approaches infinity, blah, blah, blah. Anyway, so you're going to integrate this. How do you integrate this? I can write it out. Right? Let u equals 1 over x, which you don't have to write it out. If you just tell me the answer, I'll know you can do it. Because technically, it's one you can do in your head. du would be minus 1 over x squared dx. So then our integral becomes minus e to the u du, which gives us minus e to the u. So ultimately, this integral becomes minus e to the 1 over n from 1 up to n. Right? Now what do I have? I plug this guy in. So it's the limit as n goes to infinity. Minus e to the 1 over n plus t to the 1. Now as n goes to infinity, what happens to this? It goes to 1. N goes to infinity, what happens to that? It goes to e. This means this integral converges. This means the series from 1 to infinity, e to the 1 over n squared converges by the integral test. The idea is, under the conditions that this is continuous and decreasing, the integral is a very good approximation to your series. It'll give you a larger answer than your series in general. But it's a good approximator. To the point where if this converges, that will also converge. If this diverges, that will also diverge. Right? If think that's the last thing you can do today. We'll pick up next time. But the idea is, this is sort of how it's going to be. I'm going to give you a bunch of series and ask you to tell me whether they converge or diverge. And later on, we're going to talk about absolute convergence or divergence. Test for divergence, always done first. Always look, the first thing, what's the limit, right? If it's not 0, you're done, it diverges. If it is 0, you have to do something else. Two things that you could do is the geometric series test. If you have the form, all the bases have to be constants, all the powers have to be linear, and you should be able to write it in the form a times r to the n. If you have that, then you can apply that test. Otherwise, if you notice the function is continuous and decreasing, you can apply the integral test if the integral is easy to find. There are cases where the integral is not easy to find when you do something else, right? But these are just some of the first things that you would look for. It's sort of the easier test to apply in the beginning. So we will stop there. We'll pick up next class. Well, next class is our test on chapter 12, which is just integrals. And then we'll pick up the class, maybe at the end of that class I'll pick up.